One of the special things about the Connected Microcontroller Lab is its treatment of embedded systems and their concurrency. And in this course, we step through concurrency at several different levels. Fundamentally, with embedded systems, we have this scheduling challenge. We have to share the CPU's time among multiple software activities. The software needs to all execute on the CPU. There's also peripheral hardware that needs to execute as well. One challenge with embedded systems is making sure everything happens on time. There's going to be peripheral hardware that does a lot of the work. However, there's still other work that's left over that needs to be done in software. This software needs to juggle various activities. So the CPU has to seem as if it's doing several things at the same time. So this is the challenge of scheduling. We want to make one CPU core appear to do many things concurrently. Scheduling is the question of how do we share the CPU's time among the software activities. So we look at this throughout the course over several modules. And here we're looking at Module 4. In this module, we look at task concepts, and then we look at how to improve responsiveness using finite state machines, and then we introduce interrupts. So this module has several demonstrations. So here, the first demonstration code is the demo basic concurrency project. In this application, the LEDs are being scanned sequentially. If you press one of the buttons, the LEDs will scan faster. If you press the other button, the LEDs will stop scanning. They'll all turn off. What we're looking at is the responsiveness between when a button is pressed and when the LED's scanning behavior or lighting behavior changes. So we have an example of that over here on the Wi-Fi board, and I can bring up the source code for that, and here we see the code for scanning the LEDs. Within this infinite loop, we check to see if the button is pressed, and if it is pressed, we set up the delay to be a fast delay. Otherwise, we set it to a slow delay. Then we read the second switch, button 2, and if it's pressed, we turn off all the LEDs. If it's not pressed, then we go ahead and scan the LEDs, turning on first LED 1, then 2, then 3, then 4. After each of those, we have a delay, and then we invert the state variable for the LEDs. So the next time we come through, the LED 1 will be turned off, then LED 2 will be turned off, and so forth. So we can see that executing here on the board. The LEDs are turning on in order, and then turning off in order. If I press button 1, the LEDs start flashing very quickly. They're still scanning, but at a much faster rate. If I press switch 2, then they all turn off. So with this code, we have a delay. The switches are only red after the last LED is turned on or off. So if I press the switch here, there's a delay until we get the fast scanning. Similarly, if I press switch 2, there's a delay until they turn off. Press switch 2, then they turn off. We want the switch to turn the LED off immediately, but our scheduling approach doesn't work that way. So here's a visual representation of what happens with the LEDs. So time is advancing this way. LED 1 turns on, LED 2 turns on. We press the button here, nothing happens. LED 3 turns on, nothing happens. LED 4 turns on. Finally, at this point, when we press the button here, the program reads the switch and sees, oh, it's pressed, and then changes the behavior. So we've got this delay between when we pull the switch and when we scan the LEDs. And this is an example of the scheduling problem that we have. We have the CPU executing one big piece of software that keeps the system from responding quickly. And throughout the course, we look at how to improve this. So the first step we take here is showing students how to split the software up into tasks. And the idea here is to show students that they shouldn't just put everything together into the same function. So here's the source code, the while one loop. And reading switches and lighting LEDs and turning them off, that's all put together into one piece of code here. And we show the students why it's bad, and we show how using tasks simplifies the development. And we show how to use this task structure for our LED scanner. So we have one task that reads the switches, and we have another task that scans the LEDs, and they communicate using shared variables. So we have this global variable G LED scan delay that controls how slowly or quickly the LEDs scan, and we have G allow lit LEDs, which controls whether the LEDs are blanked or whether they can be lit or not. So we have these two separate tasks that run independently, and they communicate using these shared variables. And we explain concepts for declaring shared variables and how to use shared variables. And we show how to split the code up into multiple tasks. For example, task read switches gets the code from these sections. The task to handle the LEDs gets the code from these sections. And we create a scheduler function that's going to call the tasks. In this case, we use a very simple scheduler function, which has an infinite loop, which calls task read switches, and then task scan LEDs once, and then it repeats that. So this is a simple example of a non-preemptive scheduler that's following the same task order execution. The next demonstration in this module is called Demo Basic Concurrency Tasks, and this does the same thing as the first lab, or this does the same thing as the first demonstration, but using tasks. We can open it up here in Lab 4. We select Demo 4 Basic Concurrency Tasks. We can right-click on this to set it as the main project, and we will select our processor and build it. So let's take a look at the code for the Demo 4 Basic Concurrency Tasks. And here we can see, here's our scheduler function, scan LEDs with tasks, and it calls the two tasks, first to read the switches and then to scan the LEDs once, and then it repeats. So we can build this project, and after it completes, we can download it to the board, and we can see the LEDs are lighting up once again in order. And if we press the first button, they'll scan quickly. If we press the second button, they'll turn off. But again, the switches aren't detected until after the LED scanner gets to the end of the scanning rate, to the fourth LED. So here is what the processor is doing. The task is executing our read switches and scan LEDs once, and the switches are only read between the calls to the scan LEDs once, and that's why we have such a large potential delay. If we press the switch at this time, it won't be noticed until here, which is significant. So this performance isn't much better than the previous version of the code where all the code was stuck together in one function. But this code is going to be much easier to maintain, and we're going to use it as a building, a foundation for the next steps. We look at how we can improve responsiveness so that the switch presses are detected more often, and there are some bad ways of doing this. We could insert task calls to task read switches very frequently in LED lighting code, but this is a bad idea, so we don't do that. Instead, what we're going to do is split up the code in the scan LEDs task and break it into several states so that only one state executes on each call the task scan LEDs once. The task itself is going to keep track of which state it's in, whether it should execute this code or this code or this code or this code in a particular call to this task. So we've got a state transition diagram that shows how the execution within this function proceeds from state to state on subsequent calls to the task. So we show how to create a finite state machine and put in a switch statement that executes the particular state machine state. We have demo code for this as well, and it's in the basic concurrency tasks project. So we're going to replace this function, task scan LEDs once, with the finite state machine version, the FSM version, defined down here, task scan LEDs once FSM. So we'll go into the scheduler function here and replace this. So we add FSM to change the function that's called, and we will build this, and we can download it. Okay, now that we've downloaded the FSM-based LED scanner, we should expect faster response to the switches. So instead of waiting until LED 4 is lit or turned off to read the switches, this code is going to read the switches after each individual LED is turned on or off. So we should have a much faster response. So here, we'll look when the first LED is lit, we press the switch, we get a fast response. We don't have to wait for the last LED to be changed. So this is much more responsive. And we see the improvement in turning off the LEDs as well. The finite state machine code gives us much better response because the scan LEDs once FSM function, which used to take a long time to run, now is much faster, so we're able to check the switches much more often. And this cuts down on the response delay. We then introduce the concept of interrupts. And the idea is to show that a hardware event, for example, can force the processor to stop running its mainline code and instead switch to interrupt service routine to handle the switch. And then it returns back to the main code. This is an important thing for the students to understand, and we then see how to change the task structure to support the interrupts. And what happens is we replace this pull switches task with an interrupt service routine, and that interrupt service routine will be triggered anytime either of these switches is pressed. And we will still use the same shared variables to communicate between the ISR and the task. So we discuss how to declare shared variables again, and we point out the importance of using the volatile keyword to make sure that the compiler generates correct code for these variables that are shared between an interrupt service routine and the mainline code. And we also provide a preview of interrupts and atomicity of data operations. And then we step through how to write the interrupt service routine. And we also raise some questions of how do we turn off the LEDs immediately from within the interrupt service routine? And this would make a good classroom discussion. So our demonstration code for this is in demo basic concurrency interrupts, and we're going to see much better performance here. What we'll do is select that project and set it as the main project. Make sure that we have the right processor selected, the EFG in this case, and clean and build the code. And after loading is completed, then we can program the microcontroller. So now we can see the LEDs scanning along here. If we press the fast button, they speed up very quickly. And if we press the off button, they all turn off instantaneously, or apparently instantaneously. So this is much better performance. This is what we would expect from this kind of code. And we get this because of the interrupts. Later in the course, we'll see how to use interrupts and finite state machines in order to get better performance. And we'll see the benefits of that. We will also talk about advanced interrupt topics, such as if we can interrupt an ISR, what actually happens in the CPU between an interrupt request and the ISR execution, and how does the CPU get back, how long does it take. So this module, number 4, introduces how interrupts help with concurrency. Later in the course, we get into what actually happens for the interrupt. We also look at how we can use timers to get rid of these delay calls. So hardware peripherals can tell the processor when a certain amount of time has gone by, rather than forcing the processor to execute code waiting for a certain amount of time to pass.